Okay. Today we are going to discuss about mobile radio propagation mechanisms, also the free space propagation models, and ground reflection two-ray model. Okay, this is from the module 5. So basically we are assuming that the transmitter and receiver are in line of sight, or the signal is transmitted from transmitter to receiver in a straight line. Okay, but actually the signal transmission is not in line of sight or in straight line because of many obstructions like building, mountains and trees, like that. Okay, so the actual transmitting path of a mobile radio is not a straight line or line of sight propagation, is something other than line of sight propagation. Okay, so first, what are the different mechanisms for this different propagation paths, or that is why the signals are not transmitted in a line of sight path. So the main propagation mechanisms are reflection, diffraction and scattering. Okay, the first one is a reflection. So this reflection occurs when an electromagnetic wave falls on an object which has very large dimensions as compared to the wavelength of the propagating wave. Okay, so when the electromagnetic wave falls on an object which has a large dimension than the lambda value of the electromagnetic wave, so at that case a reflection will occur. Okay, so when a radio wave falls on another medium having different electrical properties, then a part of this radio wave is transmitted into it, and some part of this radio wave energy will reflected back. Okay, so if this medium is, or the electromagnetic wave is incident on a dielectric medium, then some energy is reflected back and some energy is transmitted. If it is a perfect conductor, all the energy of the electromagnetic wave is reflected back to the first medium. Okay, this amount of reflection or amount of energy reflected back will depends on the medium and polarization of the electromagnetic wave. Okay, so this is the reflection propagation mechanism. Okay, so when a electromagnetic wave is incident on some other object which is have a large dimension as compared to the wavelength of the electromagnetic wave, the some part of the electromagnetic energy will transmitted through the medium and some part of the electromagnetic energy will reflected back from that medium to the first medium. So that is reflection. Then the second mechanism. So diffraction is a phenomenon due to which an electromagnetic wave propagates beyond the horizon around the curved Earth's surface and obstructions like tall buildings. Okay, so ഒരു curved ആയിട്ടുള്ള സർഫസിൽ കൂടി എന്താണ് സിഗ്നൽസ് ട്രാൻസ്മിറ്റ് അല്ലെങ്കിൽ ഇലക്ട്രോമാഗ്നറ്റിക് വേവ് പ്രൊപ്പഗേറ്റ് ചെയ്യുന്നതാണ് ഇത് ഡിഫ്രാക്ഷൻ എന്ന് പറയുന്നത്. ഓക്കെ, സോ as the user moves deeper into the shadowed region or the curved region, the received field strength decreases. So, but the diffraction field still exists and it has enough strength to receive the signal. Okay, that is the diffraction mechanism. Then third one is scattering. Okay, so the actual received power in a antenna is somewhat stronger than the propagation models of reflection and diffraction in the case of scattering. The cause of the scattering is trees, buildings, and lampposts, which will scatter the energy in all the directions. Okay, so the total energy received or the total radio wave energy is the sum of all the energies or all the signals in different directions, because in these obstructions, due to these obstructions, trees, buildings, and lamps, the electromagnetic wave is scattered in different parts, and the actual energy of the received signal will be higher than what we are expected from the diffracted waves and the reflected waves. Okay, so these three are the propagation mechanisms. Now, different propagation models. So, radio propagation models, which will focus on the predicts the average received signal strength at a given distance from the transmitter, as well as the variability of the signal strength. Okay, so a radio propagation model will predict the received signal strength or the received signal power at a particular distance from the transmitter. Okay, so there are two types of models: large scale propagation models and small scale or fading models. These are the two types of propagation models. First one is large scale propagation model. So in large scale propagation model, it will predict the mean signal strength for an arbitrary transmitter receiver separation distance, which are useful to estimate the radio coverage area of the transmitter. Okay. This large scale propagation characterizes signal strength over large transmitter receiver distance. If the transmitter and receiver are at a large distance or the separation is large, then this large scale propagation model is used to characterize the signal strength. Okay. So as the mobile moves away from the transmitter over much larger distances, the local average received signal will gradually decreases. Okay. In this case of large scale propagation model, the signal strength or the average received signal power will decrease gradually. That is large scale propagation model. It is it is used to characterize the signal strength when the transmitter and receiver are placed at a large distance. In the case of a mobile radio communication, it is the transmitter is or the mobile station and the receiver is the base station antenna. The next one is small scale or fading model. So this small scale propagation model that characterizes the rapid fluctuations of the received signal strength over very short travel distances or short time durations. Okay. So this small scale propagation model, or it is also known as a fading model, is used to characterize the rapid propagations or the rapid fluctuations of the received signal when the transmitter and receiver are placed at a small distance, or the mobile station is travel in a short distance and in a short time duration. So as a mobile moves over very small distances, the instantaneous received signal strength may fluctuate rapidly, giving rise to small scale fading. Okay. So we can see it in a figure. So this is the two types of propagation models: large scale fading and small scale fading. Okay. So this portion, this will represent, this x-axis represent the transmitter receiver separation and y-axis represent the received power. So this portion represents the large scale fading. So that means the transmitter receiver separation is large and the signal strength is reducing or decreases gradually. Okay. But this portion, this represents the small scale fading. Here this signal fluctuate rapidly. The signal strength fluctuate rapidly. Here you can see rapid fluctuations. This high to low, rapid fluctuations you can see. So in small scale fading, there will be rapid fluctuations, and in large scale fading, there will be gradual decrease in the received signal power. Okay. ആരെങ്കിലും കയറാൻ നിൽക്കുന്നുണ്ടെങ്കിൽ കയറാൻ പറ. ആരെങ്കിലും കയറാനുണ്ടെങ്കിൽ കയറിക്കോളാൻ പറ. ആരില്ലെന്ന് തോന്നുന്നു. ഞാൻ കണ്ടിന്യൂ ചെയ്യുക. Now we are going to see different propagation models. Okay. So first one is free space propagation model. Okay. So this free space propagation model, which is used to predict the received signal strength when the transmitter and receiver have a clear unobstructed line of sight between them. Okay. So in the case of a line of sight propagation without any obstructions, we will use this free space propagation model. It is actually a theoretical concept. In practical case, there is no free space propagation mechanisms. Okay. So we can see the received power of the radio wave, which is given by the equation PRD equal to PT GT GR lambda square divided by 4 pi D whole square into L. Things you know. This equation is known as Friis transmission equation, where PT is the transmitted power, GT is the gain of the transmitting antenna, GR is the gain of the receiving antenna, and lambda is the wavelength of the radio wave, and D is the separation or distance between the transmitter and receiver, and L is the system loss factor. Okay. So normally the value of L greater than or equal to 1. Okay. Then next is path loss. So the path loss is defined as the difference between the transmitted power and the received power in dB. Okay. So that is the path loss or path difference. Sorry. path loss is this is given by PL equal to PL in it is in dB, that is equal to 10 log PT minus 10 log PR, that is equal to 10 log PT divided by PR. So this is the path loss. So that we can write as 10 log PT into, we can substitute for PR. Then we will get the equation minus 10 log GT GR lambda square divided by 4 pi D the whole square into L. So this is the equation for path loss. Okay. So assuming that no loss at unity gain antennas, then the path loss is given by PL, which is in dB, equal to minus 10 log lambda square divided by 4 pi D whole square. Okay. We're assuming that there is no loss. That means the value of L will be 1 and the antennas have gain unity or equal to 1. Then the free space model is only valid for receiving power PR for values of D which are in the far field of the transmitting antenna. Okay. This free space model or this equation is valid for the received power of the antenna which is having a separation distance from the transmitter D, which the D should be lying in the far field of the transmitting antenna. This far field, or which is also known as Fraunhofer region, which is a transmitting antenna, is defined as the region beyond the far field distance which is related to the largest linear dimension of the transmitting antenna aperture. Okay. So the antenna largest linear dimension aperture value ഉണ്ട്. അതായത് ആ ട്രാൻസ്മിറ്റിംഗ് ആന്റിനയുടെ അപ്പറേച്ചർ ഏരിയ അതാണ് നമ്മൾ അതിന്റെ ലാർജസ്റ്റ് ലീനിയർ ഡയമെൻഷൻ എന്ന് പറയുന്നത്. സോ ഈ ലാർജസ്റ്റ് ലീനിയർ ഡയമെൻഷനേക്കാളും കൂടുതലായിട്ടുള്ള ഒരു ഡിസ്റ്റൻസ്, അതാണ് ദാറ്റ് ഈസ് ഡിനോട്ടഡ് ബൈ DF. അതിനെയാണ് ഫാർ ഫീൽഡ് ഡിസ്റ്റൻസ് എന്ന് പറയുന്നത്. ഓക്കെ. സോ ദാറ്റ് DF ഈസ് ഈക്വൽ ടു 2 into D square by lambda. into D square divided by lambda, that is the far field distance or Fraunhofer distance. Then if the distance between the transmitter and receiver antennas, receiving stations, are greater than this far field distance DF, then only this free space propagation model or free space model will be valid. Okay. So the distance D should be greater than this Fraunhofer or far field distance DF. And if D naught represents the power reference point, then the received power at a distance greater than D naught is, which is given by received power PR at a distance D equal to PR at D naught. That's the received power at a reference distance, that is PR D naught, into D naught divided by D the whole square. Okay. So this is the received power at a distance which is greater than the reference distance D naught. That is PR D equal to PR D naught into D naught by D the whole square, where this D naught should be greater than DF, that is DF should be greater than, D naught should be greater than DF and the D should be greater than this D naught. Okay. So D is the highest distance and D naught is the reference distance which is also greater than the far field distance. Okay. Then this received power PR, which is represented in dBm, that is equal to 10 log PR D naught divided by 0.001 watt plus 20 log D naught by D. So it is corresponding to the, this dBm is corresponding to the milliwatt power. Okay, so this term 0.001 watt is coming here. When converting to watt, this is corresponding to milliwatt power. So this is, when converting to watt, it is came as 0.001 watt. So 10 log PR D naught divided by 0.001 watt plus 20 log D naught by D. This is the received power when the transmitter and receivers are separated by a distance of D in the free space propagation model or Friis propagation model. Okay. So this is the free space propagation mechanism, where there is no, the transmitter and receivers are at the line of sight, and also there is no obstructions. Then next we are going to the ground reflection or two-ray model. Okay. So this is the diagrammatical representation of a ground reflection or two-ray model. Here it is transmitter and it is receiver. From transmitter to receiver, the radio wave is propagating through two paths. This is one path and this is another path. So this path is known as ground reflected path, and this path is known as line of sight path. So there will be two paths, line of sight path and ground reflected path. The distance between the transmitter and receiver is D, and height of the transmitting antenna is HT and height of the receiving antenna is HR, and the energy of the electromagnetic signal in the line of sight path is ELOS, and in the ground reflected path EI is the incident energy and ER or EG is the reflected energy, and theta I is the angle of incidence and theta O is the angle of reflectance. Okay, so this is the ground reflection or two-ray model. So this is this is 1 minute. Okay. So this is the actual representation of the ground two-ray ground reflection model, and this is for analysis. We are taking the image, mirror image of the ground reflection model. This is for the analysis, and now we will see we have to find out what is the received power in the ground reflected, two-ray propagation model. Okay. So first, the energy received or energy in the line of sight propagation path, that is equal to E naught D naught divided by D dash cos omega C T minus D dash by C, where E naught is the free space electric field at a reference distance D naught, where this separation between the transmitter and receiver D should be greater than this value D naught, and D naught should be greater than the far field distance DF. We already told that. Okay. Then D dash represents the length of the line of sight propagation path. This is the length of the line of sight propagation path, that is D dash. Okay. So this is the energy in a line of sight propagation or radio propagation wave. Okay. Then this omega C is the frequency, angular frequency, and C is the velocity of light. Okay. Then next, the energy of the ground reflected wave, EG. So Eg equal to tau into E naught D naught divided by D double dash cos omega C into T minus D double dash divided by C, where D double dash is the length of this ground reflected path. So this is the length of the D double dash is the length of the ground reflected path. The length from here to ground and from this ground to this receiving antenna. So D double dash is the length of the ground reflected wave. Okay. Then according to the according to the laws of reflection, this angle of incidence equal to angle of reflection. That is theta I equal to theta naught. So therefore the energy, the reflected energy Eg equal to tau into Ei. Tau into Ei, where tau is the reflection coefficient. So the reflected energy Eg equal to the reflection coefficient into the incident energy Ei. Okay, so Eg equal to tau into Ei. So that is represented here. So Eg equal to tau into E naught D naught divided, where tau is the reflection coefficient. E naught D naught divided by D double dash cos omega C T minus D double dash divided by C. Okay. So for small values of the angle of incident, that is theta I, the reflected wave is equal in magnitude and 180 degree out of phase with the incident wave. So the resultant electric field have the reflection coefficient tau equal to -1. Okay. So we can write the total energy E TOT equal to E LOS plus EG. So in the case of a ground reflected wave, the total energy, so it is a vector concept. So two vector components are there. So the total energy is equal to E LOS plus EG. So total energy is the line of sight energy plus the reflected energy from the ground reflected wave. Okay. So E total equal to E LOS plus EG, that is equal to E naught D naught divided by D dash cos omega C T minus D dash by C minus. So we already told that the tau has a value of -1 because for small values of theta I, the reflected wave or the energy will be in, the reflected energy will be in equal and it is out of phase, that is why tau equal to -1, and therefore this plus becomes here minus E naught D naught divided by D double dash cos omega C T minus D double dash by C. Okay. So this is the total energy of the ground reflected wave. Then the path difference delta. Delta is the path difference. So delta equal to D double dash minus D dash. Okay. So D dash is the line of sight distance and D double dash is the ground reflected path distance, and the path difference. The path difference is the difference between these two distances. So D double dash is greater. So D double dash minus D dash, that is the path difference. Okay. So in order to find the expressions for D double dash and D dash, we are using this image of the ground reflected model or this two-ray model, and we will get D double dash equal to HT plus HR the whole square plus D square. So HT plus HR this. Okay. So HT plus HR the whole square plus D square. So D is the distance between the transmitter and receiver antennas, and HT plus HR is the height of the, so HT plus HR is the height of transmitting antenna plus receiving antenna. Okay, so we have to find out this distance d double dash in order to find that distance. So this distance and this distance should be same, and that is why we are taking this portion. This portion we are taking. This we are taking in order to find d double dash. Okay. Then it is be a right angle triangle. Then the hypotenuse, length of this hypotenuse equal to this HT plus HR the whole square plus d square. Okay. So like that we can find out d dash also. So d dash, in order to find d dash, we are taking this. We are taking this, that is HT minus HR the whole square. This portion we are taking HT minus HR the whole square plus d square. So this is the hypotenuse dr, and this is HT minus HR, and this is d. So HT minus HR the whole square plus d square equal to d dash square. Okay. So we are substituting that equations HT plus HR the whole square plus d square minus, okay, d double dash square is we are getting, so root of this, and minus root of HT minus HR the whole square plus d square. Then when the value of d, the separation between transmitting and receiving antenna, d is very greater than HT plus HR, we are using the Taylor series expansion. We will get delta equal to the path difference, delta equal to d double dash minus d dash, that is equal to 2 into HT HR divided by d. Okay. Then the phase difference theta delta equal to 2 pi delta divided by lambda, that is equal to omega c into delta by c. Okay. So this is the path difference and phase difference in the two-ray propagation model. Then the time delay between the arrival of two components. The time delay between the arrival of the line of sight component and the ground reflected component is tau d equal to this path difference delta divided by c. So the time delay means that is the time taken for the wave propagate more distance in the ground reflected path. Okay, actual distance it should have to travel is the line of sight distance, but it is traveling more distance because it is traveling through the ground reflected path. So the path difference will give the extra distance it is traveling. So the time delay for the arrival of the two components, which is given by dou d equal to delta divided by c, that is equal to theta delta divided by 2 pi fc. Okay. Then as d becomes large, the difference between the distances d dash and d double dash becomes very small, and the amplitudes of line of sight energy and the ground propagated energy EG are identical and differ only in phase. Okay. When the transmitting and receiving antennas kept in a large distance, then d dash and d double dash will be approximately equal. So the difference will be very small. In that case, the line of sight energy and the ground reflected energy will be almost equal, and that will be in out of phase. So E naught D naught by D, we can write it as E naught D naught by D is approximately equal to E naught D naught by D dash, approximately equal to E naught D naught by D double dash. Then the received electric field is evaluated at time t equal to D double dash divided by C. The received electric field which is given which is evaluated at a time t is equal to d double dash by c. So we can substitute t is equal to d double dash divided by c. So we will get E total equal to E naught d naught by d dash cos omega c. We are substituting in this equation E total. Here we are substituting t is equal to d double dash divided by c. D double dash divided by c. So we can write it as E naught d naught by d dash cos omega c d double dash minus d dash by c minus E naught d naught divided by d double dash cos omega c 0. That is equal to E naught d naught by d dash cos omega c delta by c minus E naught d naught divided by d double dash. Then we can simplify it as E naught d naught divided by d dash. ആരെങ്കിലും എന്തെങ്കിലും പറയുന്നുണ്ടോ? ഹലോ, എന്തെങ്കിലും ചോദിച്ചോ ആരെങ്കിലും? Okay, we will continue. So E total equal to E naught d naught by d dash cos theta delta minus E naught d naught divided by d double dash. That is approximately equal to, because d dash and d double dash are approximately equal, so we can write it as d dash equal to d approximately equal to d double dash approximately equal to d. So we can write E naught d naught divided by d cos theta delta minus 1. Okay. So this is the equation for the total energy. Now we should have to find out the received power. Okay. So for that we are taking this vector approach. So here this is the vector E naught d naught by d double dash. This is E naught d naught by d dash, that is corresponding to line of sight propagated wave, and this is corresponding to the ground reflected wave. So the total energy E TOT, the total energy of the electromagnetic wave E total, which is represented by this. So this we can get from the trigonometric law, cosine law. So in cosine law, this A square equal to B square plus C square minus 2BC cos A. We are using this cosine law here. So we will get E total square. We are taking the modulus E total square equal to E naught d naught by d dash whole square plus E naught d naught by d double dash whole square minus 2 into 2BC. That means 2 into E naught d naught by d dash E naught d naught by d double dash cos theta delta. Okay. So we, by using this cosine law, we will get E total square equal to this. Okay. So we are taking d dash equal to d double dash equal to d. So we can rewrite it as E total square equal to 2 into E naught d naught by d whole square minus 2 into E naught d naught by d whole square cos theta delta. So that is equal to 2 into E naught d naught by d whole square into 1 minus cos theta delta. So from this we can write E total equal to is E total square, E total equal to root 2 into E naught d naught by d root of 1 minus cos theta delta. So you know 1 minus cos theta equal to 2 sin square theta by 2. So by using that trigonometric relation, we will get 1 minus cos theta delta equal to, here we will get 2 sin square theta delta by 2. So we can write it as 2 into E naught d naught by d sin theta delta by 2. Okay. So for small values of theta delta, sin theta delta by 2 will be equal to theta delta by 2. So for small values of angle, sin theta equal to theta. Using that relation, we can write it as sine theta delta by 2 equal to theta delta by 2. Okay. So using the expression for theta delta, we have already written the expression for theta delta here. This is the expression for theta delta 2 pi delta by lambda, or omega equal to omega c delta by c. So using that expression, we can write theta delta by 2 equal to 2 pi ht into hr divided by lambda t. So that is less than 0.3 radians. The value of theta delta by 2 will be less than 0.3 radians. Okay. So this total energy, E total, will be equal to 2 into E naught d naught by d theta delta by 2. That is equal to, that is the expression for E total. So that is equal to, we find out the expression for theta delta by 2 also. So by substituting that, we will get 2 into E naught d naught by d 2 pi ht hr by lambda d. So that is the final expression for the total energy in the two-ray reflection model. Okay, so the total energy of the received mobile radio signal. Okay. Then the power received at a distance d from the transmitter is given as, that is PR equal to PT GT GR HT square HR square divided by d raised to 4. That is the received power of the radio signal at the receiver. Okay. So the path loss for two-ray model is then given by PL, path loss in dB equal to, that is 40 log D. So path loss is the difference between the power of transmitted and received power, which is in dB. So that is equal to 40 log D minus 10 log GT plus 10 log GR plus 20 log HT plus 20 log HR. So that is the path loss in the case of two-ray reflection model. Okay. So this is the analysis of two-ray reflection model or the ground propagated model. So here we are find out the main thing is the total received energy at the receiving antenna, which is placed at a distance of d. Then the power, received power of the receiving antenna, also the path loss of the two-ray model. Okay. So that is all about the two-ray reflection model.